All right, everybody. Thanks for coming this morning. So I guess the good news here is that we've covered all the material that will be on the first exam. So what we're going to do over the next couple of classes is sort of look at first law problems, basically the type of long answer problems that you might end up seeing on the exam. Now, remember, the exam will be, have three parts. This is sort of typically how we run our exams, where the first part will be 10 multiple choice questions, and then you'll have two long answer problems, right? And those long answer problems are going to be problems where you look at a system and you work the first law of thermodynamics. So without getting into too much extra things or other material, we're going to look at this particular problem. So we have a piston cylinder assembly that contains 2 kilograms of water, right? So it's held in this piston cylinder assembly, and the water initially has a pressure of 1 atmosphere and 20 degrees, right? So that's over here in position 1. And then heat, we keep adding heat, right? And so as we add heat, eventually that water will expand, right? Particularly as it starts to boil. And then what's going to happen is that it will expand up until the point where it gets stopped by just the geometry of the system. So basically there's stops in here that make it so the piston can't expand anymore. So as we move from state 1 to state 2, the pressure is constant. So heat is coming in, but pressure is constant. Then we get to a point where the pressure is 4 bar, or we continue to add heat until the water reaches 4 bar. So we're going to keep boiling, and the pressure is going to keep going up, right? What we're asked to find is the total work and the heat transfer through these 2 processes, right? So it's not just a single process, it's 2 processes that run back to back. So the first happens at constant pressure, where we have 1 atmosphere, right? And the second happens after the piston hits the stops. So it's important for us to realize that at that point, it's the volume that's constant, right? So this is the starter sheet for today. This is the same material here, right? So what I've done is I said, okay, there's 2 kilograms of water, right? So here I'll write down that the mass is equal to 2 kilograms, because I don't think I did that yet, right? It initially exists at 1 atmosphere, which is 1.013, or really what I think I should do is get rid of this and put pressure as kilopascals. Remember, I said before, our lives tend to get easier when these are in kilopascals. So this is going to be 101.3 kilopascals. And this is going to be 101.3 kilopascals, right? Because we've gone at constant pressure from state 1 to state 2. So state 1 and state 2 must have the same pressure. And then this is going to be not 4 bar, but 400 kilopascals, right? Because that tells me P3, right? We're also told that the volume here is constant, right? So here, if we look at this, right? So my state table doesn't have volume, it has specific volume, but we remember that little v is equal to big V divided by the mass. So I know as I move from state 2 to state 3, the volume is constant. Now, I only know that because I'm using sort of my engineering intuition, or I'm looking at the problem. The problem doesn't specifically tell me that the volume is constant, but it tells me that at state 2, we hit these stops and we continue to add heat. So because we add heat, that steam wants to keep expanding, right? Or maybe water wants to keep boiling to generate more steam, right? So it's not condensing, which would make the volume go down, right? So what's happening here is that the volume must be staying constant, right? Because it hits the stops. Oh, that's okay. Glad you're back, right? Right. So here we moved from state 2 to state 3 at constant volume. So we know that this volume is constant from state 2 to state 3, And we know also that because this system is closed, the mass is constant the whole time, right? So if the volume is constant and the mass is constant, then the specific volume here from state 2 to state 3 must also be constant. So there's a couple things that we're asked to do. We're asked to find the work, so the total work. So we want to find A, which is the total work. I'm just going to put here work. Which is going to be the sum of work from 1 to 2 plus work from 2 to 3. B, we're going to want the total heat transfer. And the total heat transfer is going to be Q from 1 to 2 plus Q 2 to 3. And then we're asked to comment on the direction, C, so sine, right, of Q and W, right? And then we're asked to sketch on the TV and PV diagrams here. So does anybody have questions about how we've set the problem up so far? Okay, so now we're at this point where, on an exam, this is kind of the pivotal point, right? You kind of read stuff, you sort of take down the given information, right? You start to fill out the state table, but then you can kind of get into this, you can sort of sometimes fall into a black hole and you're like, I don't know what to do, right? Now, if that happens to you, and I hope that it doesn't, right? I want you to follow a particular process, right? So what do we know how to do, right? So the first thing we're going to do is we're going to say, I'm going to assume that my first assumption here is going to be that mass is constant. And the cool thing about this is once I say that mass is constant, then that means that delta E is going to be equal to Q minus W, right? Or in this case, because there's two processes, right, then we're going to say that E2 minus E1 is equal to Q1 to 2 minus W1 to 2, and E3 minus E2 is going to equal Q 2 to 3 minus W 2 to 3. So far, I didn't need to know too much specific about the actual problem. Here, I guess I split this out, right? But we could have gone just from this equation too, right? But now I got to remember, right? So there's two sort of halves of this equation. There's this half where we ask the question, what's the fluid? Right? That gives us something about delta E. There's the W part where we ask, what's the pressure volume relationship? So what's P as a function of V? And then usually we'll use the first law to find Q. So I can start to simplify this a little bit further still, right? Because I can make some more assumptions, right? So some assumptions that we'll often make, right, are that 2, I'm going to assume that the change in kinetic energy is approximately equal to 0. And then I'll wrap this up in the same equation, that the change also in potential energy, which I'll include spring energy in there for now, is also 0. So what this means is that delta E becomes only delta U, which is equal to mass times delta little u. So now, if I called this part my equation 1, I would take this down into here, right? And that's going to become, right, because I've said that kinetic and potential energy changes can be neglected. So this is going to be the mass times U2 minus U1 is going to be equal to Q from 1 to 2 minus W from 1 to 2, and the mass times U3 minus U1 is going to be equal to Q from 2 to 3 minus W from 2 to 3. Does anybody have any questions to this point? So now I got a choice, right? Really, I got three paths that I can take here, right? So there's three things that I'm going to have to do, right? So things that I don't know, right? So I don't know the U's, right? So I could fix states. I could find work. Or I could draw the PV diagrams. I think it asks for PV and TV in this case. And I think that drawing these will help me do both of these things, right? So drawing the PV diagrams will help me see the shape, right? Because remember, we know that work is the integral of PDV, right? Which is the area under the PV curve. And drawing these diagrams out will help me figure out which phase that I'm in, which will hopefully help me figure out which table I'm supposed to use. So because drawing the PV and TV diagrams, I think, can help me do both of these other two things that I need to do, I'm going to do this one first, right? And then I guess just randomly, I'll say I'll do the work second, and then I will do the, I'll fix the states last, right? And actually, this is probably not a bad strategy for an exam, because fixing the states might be the thing that takes the longest to do, right? You got to look numbers up on a table, you got to do some interpolation and stuff, and that can take a little while, right? Like I think that's basically what the last homework was about, right? So it can take a while. So I'll leave it symbolic until I sort of have to do that. I'll try to get as much done on the page before that as I can. So first I'm going to draw the PV and TV diagrams. Right? So the first thing when I do this, right? Well, first I guess I'll just draw the So now I ask myself, what's the fluid? And there's two answers, right? There's basically water and air, right? Or, basically something that has a vapor dome or something that doesn't have a vapor dome, right? So is this something that's undergoing phase change, or is it an ideal gas? Or maybe a solid too, but we wouldn't really draw a PV diagram for that, right? So in this case, it is not air, right? The problem told us that it's water, right? So we know that it's water, and because it's water, I can draw vapor domes on my PV and TV diagrams. Oops. Now, I generally do encourage people to bring colored pencils to exams, but you don't have to. Right? So what do we know? If I go back up to my state table, I think what it tells me, right, is that if I looked at temperature, pressure, right, and I had here state 1, 2, and 3, because we want 3 processes here, right, and specific volume, right? I think the temperature initially was 20 degrees Celsius. The pressure was 1 atmosphere, so 101.3 kilopascals. From 1 to 2, this is 101.3 kilopascals, and this is 400 kilopascals, right? And we know that V2 is equal to V3 over here. So how can I start to draw these things, right? So first, on a TV diagram, so first I know that my temperature is 20 degrees. I know that 20 degrees is certainly less than this maximum temperature, right? This is like 375, I think, the critical point, critical temperature for water. But I know water can exist as a liquid at 20 degrees because I've seen it, right? So this is my constant temperature line, right? This is my 20-degree line. For pressure, right, that same 20-degree line is going to come down over here. It's going to cross the vapor dome, and then it's going to go down again, right? But then I know also that at 1 atmosphere, right, 1 atmosphere, what temperature does water boil at 1 atmosphere? 100 degrees, right? 100 degrees is bigger than 20. So here, if I wanted to draw a line that was a constant pressure line, right, that was 100 degrees. So this is P is equal to 1 atmosphere, right? So over here, we know that this would line up with 100 degrees over here, right? So my state 1 is over here, right? State 1 is a subcooled liquid, right? So we know that for sure. We could see that over here as well, this temperature line, right? If where it's constant is 100 degrees, right? If this was my 100-degree line, would go down like this, right? This is where this would be 100 degrees. So then 20 degrees has to be down here somewhere, right? Oops. How about I start this again, right? So basically, this is so there's going to be some temperature line that corresponds to 100 degrees, right? That's this green line here, right? And now I know that my pressure here is 1 atmosphere, and this 1 atmosphere line is going to cut through the vapor dome at the same place as this 100-degree Celsius line, right? So this is 1 atmosphere. This is 20 degrees Celsius. So this point here on my PV diagram is here. This is state 1, right? So state 1 is subcooled liquid in both cases. So this is a subcooled liquid. That's good, right? You don't want to be in a place where we're not sure. Right, now state 2 is a little trickier. We know that heat goes into the system, and we know we're still on this 1 atmosphere line, right? So this is 1 atmosphere. We're adding heat, right? So what's going to happen is if we add heat, the temperature is going to go up, right? And then we're going to start to boil, and then we're going to get superheated vapor. So I don't know where state 2 is. Right, state 2 could be over here, right? Let's call this 2 prime, right? But it could also be somewhere over here, 2 double prime. I don't know if it's under the vapor dome somewhere or if it's superheated vapor, right? So it could be over here, right? This would be 2 prime, or it could be, if we were still at constant pressure, 2 double prime. So we don't know if we've gone past the edge of the vapor dome. We do know, though, that we have started to boil, because we know that liquid water is incompressible, right? That the density doesn't change very much as we increase the temperature of the water from 20 degrees at 1 atmosphere up to 100 degrees at 1 atmosphere. So then we know that that water hasn't really expanded any. So in order for it to start pushing that piston out, we've got to generate some steam. So we know that we have some vapor, but we don't know if we're here or here, right? So now I can draw, if I know from state 2 to state 3, we're at constant volume, right? If the specific volume is constant, then we know that we have to be up or down on these. We'll pretend that these are vertical lines. So now state 3 is a 3 prime is somewhere on this line, right? And 3 double prime would be somewhere on this line, right? So we don't know exactly where this point is, but I know it's got to be vertically up or vertically down from this line. So this didn't help me a ton, right? But it helped me at least a little bit, right? So what I think I need to do is I'm going to try to find state 2, right? So how can I do that, right? So the first thing is, the good news is I can go up here and I can totally fix state 1. So I think I'm going to change, even though my original idea was to fix the state's third, I'm going to change my plan, right? You know, there's a good lesson in life, I think, that, you know, people say that plans aren't worth very much, but planning is super important, right? So here we're constantly evolving as we get new information, right? So now I'm going to try to fix this state second, because hopefully then that helps me draw my diagrams better, which then help me find the work, right? So then maybe I'll do this third, and maybe I'll change my mind again, right? But for right now, what I'd like to do is find out where state 2 is. So here, the good news is I know that this state 1, when I was drawing this, was a subcooled liquid, right? That means that this is approximately going to be VF at 20 degrees, which is going to be approximately 1 over 1,000. We'll look that up, right? And this is going to be UF at 20 degrees. Right? That's how we'll approximate that. So this I can find. I don't know the number yet, but basically I have found this value. Right? So these two things I basically know. Anybody got an idea of how we can find the specific volume at state 2? Because that's going to be how we fix this other state. So we need some kind of information about how to find the specific volume here. Oh, you know, it's not on this sheet, I think. Let's go back to the PDF, or to this, right? So I think here we were told some information about the diameter of the cylinder and the length of the cylinder. So if we know that the diameter here is 2 meters, right, and the length is 1 meter, then I could find the volume, right? And I think I know something about the mass of water because there's 2 kilograms of water. So if I knew the volume and I knew the mass, then I would know the specific volume. See how that makes sense? So what I can do, so the diameter is 2 meters and the length is 1 meter. So I can go down here, right? And I can say, I can find V2 is going to be equal to V2 over the mass, right? But V2 is going to be equal to pi. Now, I could say pi d squared over 4 times L, or I could say pi r squared times L. I like this version better because here I know that r is equal to, my diameter was equal to 2 meters, so r is equal to 1 meter, right? And L is also equal to 1 meter. So this volume is going to be equal to pi times 1 meter all squared times 1 meter, right? Which is just going to be pi meters cubed. But I don't want the volume, right? I want the specific volume. So V2 is going to be equal to the volume at 2 divided by the mass, right? So this is going to be pi meters cubed divided by 2 kilograms, which is going to be pi divided by 2 meters cubed per kilogram. Now, if I just whip out my calculator here, so that's going to be 1.57 approximately, equals about 1.57 meters cubed per kilogram. So this is going to be V2. It's also going to be V3. Oops. I'm not going to draw a box around it. You can see I'm not good at drawing straight on the board either. Right? So this is going to be 1.57 meters cubed per kilogram. So this is 1.57. Oops. This is also 1.57. So now the good news is over here, I know two, right? So, right, in order to fix a state, we need two independent intensive properties, right? We had that for the first state. We had two properties, and because it was subcooled liquid, they ended up being independent, right? But now, at the beginning, we only had one intensive property for state 2 and state 3. But now we know the pressure and the specific volume for both of these cases. So what do? Right? So now I'm going to fix state 2. I know that the pressure is equal to 1.013 bar, which is equal to 101.3 kilopascals. I also know that the specific volume is equal to 1.57 meters cubed per kilogram. Now my question here, right, from when I was drawing these graphs is my state 2, is it under the vapor dome or is it past the vapor dome? So the question that I'm asking here is, or I can say if V2 is in between VG, so it's lower than VG, but bigger than VF at 101.3 kilopascals, then this is two-phase. If it's two-phase, I'll find X2 and I'll use X2 to find U2. If VG is less than V2, then what this tells me is this is a superheated vapor, and what I would have to do is find the right subtable and interpolate. So let's check. So we need to find a table where the pressure is 101.3 kilopascals, but I'm not actually going to look for that. I'm going to remember that the saturation temperature in this case is 100 degrees Celsius, right? So we could, that's 100, not 10, 100 degrees Celsius, right? So what I'm going to do on this worksheet, there were different tables. These are the tables. If you ever write in the FE exam, so if you want to be officially an engineer after you graduate, get a stamp so you can so be an engineer of record somewhere. There's two different exams that you have to write. One is just so that you to demonstrate your understanding of the material that you're supposed to learn as an engineer. So people write that. That's this FE exam. Oftentimes, if people want to do that, they'll write that exam maybe in their last year of undergraduate or right after they graduate, while you're still used to taking tests and some of this stuff is still fresh in your mind. But then there's also a legal exam that you have to take. I think you might have to be working for a little bit before you take that exam. but I'm not exactly sure. I grew up in Canada where the rules for accreditation are a little bit different, but that's where these tables are taken from. They're taken from that FE handbook. So here, we're going to look at this row, right? So we know the temperature here is 100 degrees if we're under the vapor dome, but the pressure, this constant pressure line, is 101.3 kilopascals. Now we have a specific volume of, what was it, 1.57 meters cubed per kilogram. I think that's correct. Right, so here, right, this is bigger than this number and smaller than this number, right? So this is good news. This means that we are two-phase here at state 2 because we were in between these two numbers. Right, so here I'm going to go back here. Maybe you know what I'll do to make my life a little easier. I'm going to drag this table up so I don't have to bounce back and forth so much. So here, I would like to be able to read it. What I can do, format, I'll crop this a little bit so that we only have the information that we want, which are the V's and the U's. And I'll just drop this guy down here. So we know now that we're in this case, right? That VF was in between, or V2 was in between VF and VG. So for this state, we're not here. So what we want to do now is we want to find X2. Right? So we remember from our quality equation, right? Eventually we're going to want to find the specific internal energy. So I can write, you know, U2 is equal to UF plus X2 times UG minus UF. But if I look at this equation, the good news is I can pull up UF and UG, right off the table, but I don't have X2 and I don't have U2. So I can't find the specific internal energy yet, right? I got to look for another property that I know, right? Because here I don't know UF and UG. So instead, what I have to do is I have to write out this equation again, but for specific volumes. V2 is equal to VF plus X2 times G minus UF. Now in this case, I don't know X2, but I do know V2, right? I used this from the geometry, so I know all of this. So now I can rewrite, I can say that X2 is equal to V2 minus VF divided by, this should be V's, VG minus VF. I know all of these things, right? And I can see for 100 degrees, right? Here's VF and VG. So this I can rewrite as 1.57 minus, I'm just gonna say 1 over 1,000 here. I'm gonna, because my number's not gonna change very much if I don't take the, what is this, the 5th and 6th decimal place here. So this, I'm just gonna say 0.001 divided by 1.673 minus 0.001. If I was going really fast on an exam, I might just take 1.57 divided by 1.673 because this is basically going to be the same number. But here, I don't know if anybody has put this into their calculator. When I did this, I got I did it all in a different order, right? Anybody get x2? Here, I'll just work it out on my calculator here.
I got 0.938.
That to me seems close anyway, right? Because we're certainly most of this. So this is 0.938 x2. So now I can take x2 and put it back up into this equation, right? And I can say that u2 is equal to uf plus x2 ug minus uf, right? So this is going to be my uf is here, 418.94. These are all in kilojoules per kilogram, except for quality, which has no dimensions. 0.938 times 2087.6 minus 418.94. Here I get that number can't. Let's try this on my calculator. So I get 2087.6 minus 418.94 times 0.938 plus 418.94. So I get 1,984.1 kilojoules per kilogram. So this number, it makes sense, right? Because it's got to be in between 418 and 2087, right? And it should be closer to 287, right? So this 1984.1, I can put this into my table. So the next thing that I want to do is I want to ask the same question at state 3, because now I fixed state 1 and state 2. Now at state 3, I got to ask this same question: are we two-phase, or are we superheated vapor? Because now I know my state 2 is here, so it's not this 2 prime. But I don't know. I could go up to a point where I become superheated vapor over here. I don't know if my state 3 is going to be over here, or over here, right? It could be under the vapor dome. It could be over the vapor dome. So I have to ask the same question, but now I'm going to look at a different row on the table where my pressure is 400 kilopascals. So I look back at the tables, and it doesn't really fit, but they gave me a superheated water table for a pressure of 0.4 megapascals, which is 4 bar. So I'm going to copy this table up. So now we know that we have a pressure. So this is, I guess I'm hoping that this is a two-phase, or that this is a superheated vapor, because that's the table that they gave me in this problem, right? So this is, we know that state 3 has a pressure of 400 kilopascals, or 4 bar, or 0.4 megapascals. And I know my specific volume is 1.57, which is in between these two numbers here. So I know that I'm in between 1,000 and 1,100. Right? So now I can define my interpolation factor A is going to be, again, I'll take the number that I know, 1.57 minus 1.4685 divided by 1.584 minus 1.4685. Again, on a test, I might just take this value here at 1100 because it seems pretty clear that we're going to be a lot closer to this 1.584 than we are to 1.468. Minus 1.4685 divided by 0.4685. Here I got 0.88. So now I'm going to turn that around, right? And I know that my U value also has to be between these two values, much closer to this one. So now that I know A, I'm going to say that U3 is going to be equal to, this is going to be U min plus A times U max minus U min, right? So this is going to be 4052 plus 0.88 times 4256.5 minus 4052. Times 0.88 plus. Just for your, I don't know if you care too much. So the way I always do these on my calculators, I take this difference, I multiply it by A, and then I add this. I don't know if that's better or worse, but that's the way that I do it. 4231.96 kilojoules per kilogram. So this is 4231.96 as U3. So now we fixed all our states. 4231.96. So what we also did was we figured out $31.96, right? So this is good. UF, I can just grab this from the table as well. So this is UF at 20 degrees. Here I can say, okay, so I'm at 20 degrees. I can approximate this because it's a subcooled liquid, even though it's not a saturated liquid, right? It's going to be approximately this, 83.95. Right, so now I have all my U values, which is pretty good.
I have a quick question.
Shoot.
So when you're approximating, because it's a subcooled liquid, you can do that for all of the different properties, right? Like enthalpy and specific volume.
Yes, except for temperature and pressure, right? So,
Right.
Yep, yes, but all the other properties, that's reasonable to do.
Okay, all right, thank you.
You're welcome. So this is good. Now we fixed our states, right? We don't have this information yet, though, right? So let's finish our TV and PV diagrams, right? So we know our state 3, because it was a superheated vapor, right? Because basically V3 was on that superheated vapor table. So state 3 is over here or up here, right? So now I want to think about my PV diagram because my next job is to calculate work, right? So the area under this curve, right, under this line here, so this is my first process, and this is my second process. So this is going to be the work from 1 to 2. And the work from 2 to 3, because the volume is constant, the area under this vertical line, if we pretend that I drew this line vertical, is going to be 0, right? There is no area under a vertical line. So if the volume doesn't change in a closed system, then that means the work is 0. So here I know that this work is 0, and this work is going to be the integral of P from 1 to 2 dV from V1 to V2. But because this pressure is constant, this is just going to be P1 times V2 minus V1. I'll work that out down below. So here, as we go from state 1 to state 2, work, because pressure is constant, is just going to be P from 1 to 2, because it's only one pressure, times V2 minus V1. Right? Here, what we could do, we could do this either way, right? We could also say pressure from 1 to 2 times the mass times V 1 to 2 minus, or sorry, the specific volume at 2 minus the specific volume at 1, right? But I'm going to go this way. Either way should give you the same answer. So this is going to be 101.3 kilopascals times, now my volume changes, right? So this is going to be pi times d squared, right, or r squared, right? This is going to be 1 meter all squared, right? Now, the volume at 2 is going to be based on L2, which was 1 meter. Oh, see, we can't do it this way, right? Because we don't know the original position of the piston, right? Minus, we don't know what L1 is. So we're going to have to, we could use this method. So this method 1 didn't work, right? Because there's too many unknowns, because we don't know L1 and there's no way we can really find it. So instead, I'm going to use this other method, right? Here I'm going to say that P 1 to 2 times the mass V2 minus V1. So we know that this is 101.3 kilopascals. The mass is 2 kilograms. V2, this is the 1.57. V1 is going to be, we'd find this, right? So this would be VF at 20 degrees Celsius. So when we put that in, we would know the work from 1 to 2. We also know that work from 2 to 3 is equal to 0, right? So that the work total is just going to be the work from 1 to 2, right? And then we'd look at this sign. We know that work in is positive, so work out is negative. Here, because the system, the gas is pushing the piston out, I'm expecting this value to be negative because the piston is pushing, right? Because the volume gets bigger, right? So this has got to be, I wrote whip down, which is wrong, right? So it's when work in is negative, that means work out is positive. We know that work out is positive, so I'm expecting V2 to be bigger than V1. right? This is going to be about 1/1,000, right? Which basically doesn't matter in our equation, right? So we could work this out. My units here are meters cubed per kilogram, right? This is going to be in kilograms. So then we're going to multiply by meters cubed per kilogram. Kilopascals is kilonewtons per meter squared. So the kilograms here cancel. We get kilonewton meters, which is kilojoules, which is what we expect for work. Right, so the units here are going to work out. And then what we do is we use the first law to find Q1 and Q2. So we know that the mass times U2 minus U1 is equal to Q1 to 2 minus W1 to 2. And we know that the mass times U3 minus U2 is equal to Q2 to 3 minus W2 to 3, and this is 0. So we expect, the problem told us both times that heat was added. So we expect Q1 to 2 to be bigger than 0, and we also expect Q2 to 3 to be bigger than 0, right? And we can do this. I won't go through it now because we're already over time, but we have all the information here except these values of Q, which you can then just add up. So you can go to like the thermal shorts video if you want to see the numbers, but that is how we go through and do this problem. Hopefully, kind of slowing down and showing you the process helps as well. So I will stick around for a couple minutes if people have questions. Otherwise, I'm happy to let you go.
Well, have a good rest of your day.
You too. Thanks.
Thank you.
Thank you.
No problem.
Thank you.
Yep.
Hey, Professor.
Sure.
I have a question about the exam.
Yep.
I was wondering, so exam 1 covers from chapter 1 all the way to 4? Or
I'm not sure how it maps out in the textbook, honestly. Basically, all the stuff that we've done. So, you could see multiple choice questions that cover things like, the pre-work material. There could be multiple choice questions on that stuff. And then other than that, basically everything is building to what we've done here, right? So do you know how to find work? It's the integral of PDV, right? Do you know how to fix states for steam like we did today? Or next class, we'll do an example with ideal gases. So that's kind of, it doesn't sound like much when I say it in 2 sentences, but it's enough.
Yeah, it's a lot.
Yeah.
All right. Okay. Thank you.
You're welcome.
Have a good day.